It's my pleasure to welcome George Fairbanks. I think George is already signed up. Hi, George.
Hello.
Great to see you again. And
yeah, you too.
Software engineers at Google, and it's going to have a very interesting talk. But I wanted to touch a bit on something because you also wrote a book that's called Just Enough Software Architecture, right? And it's a nice title to it. So how detailed do our software designs need to be, and how do we know it's enough?
Thank you for asking that. That's one of the reasons I wrote the book. Is the book is like 10 years old now, okay, and so the world has changed in a decade. But 10 years ago, we were still reading software architecture books, and the really bright people that had written those books had, in many cases, been funded by military projects. So imagine the kinds of things you have to do if you need to assemble an enormous number of subcontractors to build literally a battleship or software system that'll integrate radar and where are my people and the communications. Like, you imagine the staggering size of that project, and then you look at the techniques that they use, right? And so the techniques are perfectly appropriate for staggeringly large engineering efforts, okay? And so here we are in the late 2000s, and I'm looking at the projects that I'd worked on, which were not large battleships, okay? And so then I said, look, guys, really, you need to be taking a look at the risks that your projects are facing. And you can pick up, like out of the goodie bag, these architecture techniques, and you can apply them. And you can stop at some point. You don't have to do everything. You can just do the ones until you go, all right, I think my risks are low enough. But the only thing that's reckless is if you knowingly don't look at the techniques, or you just rush in and throw caution to the wind, right? So how do you get the balance between them? And so that was my motivation for writing the book. I think a bunch of the ideas in the book at this point, good teams have internalized them. Yeah, people take it as common knowledge that you would like the whole team to understand the design, as opposed to like one person sitting in the corner. Right. However, I do want to make one additional point, coming on the heels of Kevlin's talk, is that a lot of people like to talk about the job roles, okay? And they also love to talk about the process, like when do I design? Do I design early? Do I design late? Do I prototype and then revise, right? Those are the topics just being discussed. Critically important. However, what I love to chat about, and what I'm going to chat about in my talk today, and what I chat about in the book, is let's put aside the job roles. Let's put aside the process that we use for the most part, okay? And say, like, if I leave that aside, what is the engineering idea that's still sitting there? Because if I see a Prius drive by, I go, oh, that's a hybrid car, right? If I see a Porsche 911, I go, oh, that's an internal combustion car. And if I see a Tesla, I'm like, oh, that's a battery car. And I don't know how they organize their teams. I don't know if they have a chief architect. I don't know if they did short iterations or if they did big design up front. But I can look at the engineering artifact and I can talk about the characteristics of battery vehicles are good for these things, but you have range anxiety, okay? So that's really what I focus my energy on, because we can talk for a long time about process, and the process is highly dependent upon your team, whereas battery vehicles always have a known set of trade-offs, right, at any given point.
Cool. And then also, because we were discussing about your talk earlier, it's about how to define or describe architecture to peers or other people. And now I'm also taking a quote from Kevlin's talk. Actually, he mentioned a quote from Martin Fowler saying that, yeah, architecture is a term that lots of people try to define, but then with little agreement.
So, that's true. And unfortunately, if you go take a look at the writing about software design and software architecture, there's unfortunately two groups, broadly speaking, and they unfortunately don't read each other's writing. And that's not healthy, okay? So there's one group that came out of, well, there's a lot of Carnegie Mellon and software engineering authors, and they wrote a bunch of books specifically about software architecture starting in the 90s, okay, in the early 90s. And the topic of software design, and there's a group of people that came out of the OO community, the Martin Fowlers of the world, and so forth, that these people came up through OO design, and then they moved into software architecture, okay? And I think that part of the reason for the schism is that the people that were doing OO were very interested in agile approaches, in how can I get in and do it right now. And especially in the 90s, like I said, the literature was about how to build battleships reliably. And that wasn't the problem that they were confronting. In the late 90s, early 2000s, people were looking at how do I build websites well? And I don't mean like the biggest company, megacorp.com, but just, you know, my mom and pop.com. Like, what are the techniques that are appropriate for that? So I think that's why the schism happened. However, I don't really believe there's a huge disagreement in the community about what architecture is. Okay, that is, it's some abstraction of the structure of the system and the relationships between things. Okay, so like I might say this is a client-server system, and that eliminates a whole bunch of details about how the files are organized and so forth, right? It's like, it's just the conceptualization of it. And that is as opposed to, say, a peer-to-peer system, which has an equal relationship between the nodes, whereas client-server, one calls the other, but the server doesn't call the client. That's the rules of the game. That's what that architecture is about.
All right, so then let's, you have the floor.
Okay,
and
let's see if I can muster the
with your
technology to make it all work. So if I go here and then I say, no, I want to say share screen. Sorry, I don't do Zoom every day. And I do that. And it looks like you guys are looking at my screen. Is that right?
Yes.
Yep.
Okay, fantastic. Okay, well, thank you very much for inviting me here. It's a great pleasure and a great opportunity because we have something that I'd like to share with you that traditionally has been very hard to understand, which is what is software architecture. The thing is that software architecture is easier to understand if you have 10 years of experience. Say, I can refer to, hey, you know all those systems you built? You can sort of think about them and zoom out and see the commonalities and the differences between them. That's very difficult to do if you're a brand new engineer, okay? If you're still an undergraduate, or maybe you're having your first job and you don't have that many systems you've built. It's hard to reflect on those. So my goal with this talk is to explain software architecture without having to refer to systems that you've already built. And so I hope at the end you will understand this and appreciate why it's so important. And I gotta click on the right window and then the slides advance. Yes, okay. So before Copernicus, people were gazing out at the stars and they built diagrams like you see here. This is a diagram of the planets and it shows cycles and epicycles, okay? In this particular model, they have the stars revolving around the Earth instead of around the sun. And as it turns out, that created an enormous amount of confusion. If you were the top of your game, the top of your field, you could understand what was going on 500 years ago with this. But can you imagine if somebody came to you and said, okay, this is a great model, now add a comet trajectory to this? Like it would, maybe if you could do it, it would be incredibly tedious. But what you'd really like is Copernicus's model, okay? There's a perspective on that same thing that's going on that makes things so much easier to understand. Now, if I ask you to bring a comet trajectory into this, it's almost straightforward. You can figure that out. The point here is that the change of perspective didn't change the solar system, but it made what was going on easier to understand. So the question is there a similar perspective you can have on software that would yield that kind of reduction in complexity, that kind of clarity in terms of what's going on? I believe software architecture is that perspective, okay? It may not be the last word, but it is the current abstraction that will help you best reduce the complexity in your systems. Software architecture is a competitive advantage. And the reason for that is that software is always getting more complicated, and that's not by accident. We build software up to the level of the complexity that we can maintain it, okay? Here's the thing. If the person next to you or a competitor starts to master software architecture and they are able to build more complicated, more sophisticated systems, they're able to succeed with larger and larger systems when you are not, or you're slow at doing so, well, it puts you at a competitive disadvantage. So software complexity has always been the #1 enemy of software developers, and it always has been, it always will be. So as software systems get more complex, software architecture is what we should turn to keep that down. So, as I mentioned in this talk, I'm going to talk about software architecture without referring to your past experience. I'm going to do that in 3 sections. The first is there's a great case study that was done by Rackspace, and they explained how they built some system 3 different times. It was the same functionality, but they built it 3 different ways. That's a great way to glimpse what the software architecture is. The second part of the talk is going to be a timeline of the architecture insights. That is, those aha moments when we went, oh, it's not as simple as this, it's actually this other insight. And then finally, we are going to ourselves do a walkthrough of a system. We'll keep the requirements the same, and we'll design it a couple different ways and see how that works out. What I'm hoping at the end of this talk is that either this will be your first understanding of software architecture. That is, you go, aha, I get it myself. Or if you already know software architecture, you can use this talk or the ideas in this talk to explain software architecture to someone else. So in this first section, I have 3 goals. First is I hope that you can glimpse the software architecture abstraction. Second, you can see that the architecture is tied to particular qualities like speed or reliability. And finally, that there's no perfect architecture. It's always about trade-offs. So Rackspace is a hosting provider, and they had a problem. People would call them up to their customer service representatives, and they would say, I'm having some problem with my email server that Rackspace was hosting. And they would work with that customer service representative to diagnose the problem, okay? And so they built a first version of a system to do that. That first system used the email servers themselves to hold on to the log files. What they did was they wrote a script that would SSH into the email servers and run the same grep expression across the log files that lived on each one of those servers, and then compile all the results back together and hand it to the customer service rep. So this way, if you're calling up and you've got a problem, the customer service rep would concoct a new query on the fly and would query the live data from each one of these machines. The problem that they had is that running a query on the machines takes a little bit of time on the machine, time that was supposed to be spent serving email. And so as their number of customers grew, they found a number of calls into the help center increased. And over time, those email servers were spending more and more of their time running the greps instead of actually serving the emails. And they're like, we can do better than this. So their second version, they left the data in log files on the server, but every so often they would push them up to a MySQL database. Now, the customer service rep, instead of running grep queries on each one of the email servers, the queries would run against a MySQL database. Of course, that's a data structure that's optimized for doing queries. It's already in relations, and we have an SQL query language to do this. Now, this worked great for a while. But the problem is, as their business grew, as they had more and more of these email servers, they eventually had the problem that MySQL itself started to have performance problems, okay? That occasionally they would cause the system to fail, and it would take longer and longer to load up all the data from the email servers into the database. So you had to wait longer and longer before you could actually run a query. So in the old system, you could run the query right away. In the new system, it scaled to many more servers, but sometimes it fell down and you had to wait a little bit of a while. So they did another change. Instead of using a MySQL database, they used Hadoop. They streamed the email logs, not kept them local at any point. They streamed them directly into the Hadoop distributed file system. And then periodically, every 10 minutes or so, they would run a MapReduce job that would index all the log files. And then that way, they could still run an SQL query against the index. Now, of course, the problem is that the index is at least 10 minutes old, and it took about 10 minutes to run. So the staleness of the query was maybe 10 to 20 minutes. Okay, so let's take a look at those 3 systems. And let's take a look first at the data freshness. In the first version, you could run a query against completely current data. In the second version and then the third version, you had to wait for the data to either be loaded or to be indexed, and that took 10 or 20 minutes. In terms of scalability, the whole reason they changed away from the first system is that it only really scaled to dozens of servers. After that, they found that those servers were slowing down. In the second system, it scaled up to hundreds of servers. But the problem is eventually that single MySQL box became a bottleneck, and it wasn't reliable. It was a single point of failure. And even though they got to hundreds of servers, they had troubles there. And the third system, they, at the time of their report, hadn't had any scalability issues. And then finally, in terms of the ability to write a query on the fly, in the first one, assuming your customer service reps could write a regular expression, they could write a query across the current data, like a customer calls and they can say, yes, I'm looking at the log files right this second. In the second and third examples, they had to write an SQL expression or a MapReduce program. Now, an SQL expression probably is even easier to write than a regular expression, so that was not much of an impediment. But what they found was their customer service reps were not ready to drop down to Java and write raw MapReduce programs. Okay, this was not something they were ready to do. And even if they could do that, the time it takes to bang out an SQL query or regular expression was way less than it was to create a custom MapReduce program. So basically, if the system didn't already support the query you wanted, it wasn't really easy to add a new query to it. So the thing that I want you to see from that is you hopefully glimpsed the architecture abstractions that we saw, and we saw that it wasn't that any one architecture was perfect. They all had trade-offs between them. So that was the case study. Let's take a look next at the aha moments that people have had over time. The previous speaker, Kevlin, mentioned several of the same points that I'm going to mention here, which was a delight to me that we came up with the same topics. So here they are. So just read this and I'm sure you can figure it out. No, just kidding. What I'm going to do to try to make this big pile a little bit more comprehensible is I'm going to group them. First, I'm going to show you what happened as far as we understood interfaces better and better, how we understood views better and better, then patterns, and then finally structure. So first, let's take a look at interfaces. Interfaces are probably one of the first things that we figured out when we did software development. Back in the 1940s, we first invented the subroutine, okay? And as soon as we invented the subroutine, very quickly we understood that the same interface could support either a fast implementation, maybe that used very little memory, or a slower implementation, a fast implementation that used lots of memory, or a slower implementation that used very little memory. And of course, we had very little memory on the machines back in the 40s, so this is a really big deal. The point being is that even in the 1940s, we were separating out different qualities of the implementation separately from what it does. So for example, if it's a sorting algorithm, it might be fast and use lots of memory, or it might be slow and use very little memory, and you might have to make that trade-off. The next thing that happened, and it was at least in place by the 1960s, is that people were separating their interfaces from their implementations. And we know this was the case because in Algol 60, it separated the idea of a compiled unit of a program from the linked program that was the final one. And so in that way, you could have one library, for example, that had the fast uses a lot of RAM implementation, or another library target that has the slower uses little RAM implementation. But the really interesting thing, and you also heard this in the last talk, was in the 1970s with David Parnas. And what he said was simply having the same interface and two different implementations is not enough to really give you what you want as far as how you divide up a system into modules. If you really want to encapsulate things and really preserve your ability to change the implementation later, you have to decide in advance what it is that is your secret. That is, what is the decision that you might want to change? And if you keep that behind the API, you're in better shape. You contrast that with what we still do today sometimes, which is we put two fields on a class like X and Y, and then we instinctively put getX and getY on that class. So having getX and getY, technically speaking, allows you to have the interface implementation split. It's not very much of one because you're leaking those details across the API boundary. Okay. The next group of insights that we had involved views. Now, in other branches of engineering that you're familiar with, we use lots of different views, not a single view of the thing that we're building. For example, with a house, you might have a top-down view of the house, the front view of the house, and going a little bit farther afield, you might have an electrical view of the house, like where the circuits are going. Or it might be the heating and air conditioning view of the house that would talk about where the duct work or how the heat moves around over time. Okay, so the idea of using multiple views was already around, but In the 1960s, the people that were very excited about structured programming made a specific insight. And what they said was, the way we write programs today makes it hard for us to imagine what happens at runtime. So the two different views are the static view of the code and then what you're imagining, which is the dynamics of the code at runtime. And they said that if we constrain the way that we write our programs, that is, use structured programming, and we don't use go-tos as just one example, it becomes way easier for us to imagine and get certainty about what's going to happen at runtime. So that was a big jump, right? That we had to think about two different views, and that we changed the way that we write code to make our thinking across those views easier. In the 1990s, there was just an explosion of these different views. People were understanding there weren't just static and dynamic views, but there's a famous paper by Philippe Cruchen who wrote about the 4+1 views, okay? And that would include things like concurrency. Now, if you had two equivalent systems and one was single thread and the other was multi-threaded, you have a whole different set of issues at hand. And so when you're viewing the system, you would like to know which things run in their own threads or their own processes. Okay. Another one that is very relevant to us today is a deployment view. Now, if I rewind the clock, say 25 years, if you wanted to know what version of, for example, the schema is on our database server in production right now, you got to go walk over to that person's desk and say, did you install the security updates and did you install the current schema? And they'd say, oh no, actually I didn't get around to that. Okay. So in order to get that idea, that view of the deployment, like what is running in production, you probably had to go around and talk to people. We do a much better job of that today, right? Because we've automated our processes by which code moves into production, okay? So that has been a huge improvement. The final insight, or at least on this list, that came about views was the idea that some views are irreconcilable. And this is an important distinction. So take that static and dynamic view. You guys remember the halting problem. The halting problem says, if you take a look at a program, you can't be confident that this program is going to ever terminate because it might have an infinite loop in it, but we can't prove that it doesn't, okay, at least for a lot of programs. When we start looking at software architecture views, that kind of problem comes up over and over. So for example, when I talk about the deployment, if I am looking at my source code, it turns out I can't understand what's going to happen at runtime, yes, but I also don't necessarily know where that source code is deployed. And I really need that in order to reason about the system, okay? So you have all these different views that are not reconcilable. An analogy of this going back to the houses is all those views that we talked about of the house, the top down, the front, the electrical and the heating, all of those at some point are reconcilable. They're all sort of three-dimensional views of the system. However, there are other things that are relevant for your house. For example, maybe the size of your house affects how many taxes you pay. Or depending on where your house is, you may or may not be allowed to have goats or chickens in the backyard, okay? These are zoning kinds of questions. It's not clear how I put that into my three-dimensional model. Like, it's a very important view, but hard to figure out. Your software might have regulations that apply in one country, but not another. It's hard to put that in the source code view of the model, of your system, okay? So this was a big deal. The next group of things we're going to take a look at is patterns. Patterns obviously all started with Christopher Alexander, who is a building architect, and started describing that many architects just design things in a tree structure, but that's actually not the way that we see stuff built in practice. The things that we really love in practice have patterns, and the patterns kind of interlock in interesting and complicated ways. And so the OO design community really picked up on this, and they talked about design patterns and so forth. The architecture community followed right after, okay? So by the early 90s, the software architecture community, led by Mary Shaw and Parnas, not Parnas, Clements, had created catalogs of the architecture patterns. In fact, they wrote a funny named paper called A Field Guide to Boxology, because they had seen lots of systems described with boxes and lines, and they were just trying to bring order to the chaos and say, we think there's a handful of these different patterns. The thing that came right after you come up with a catalog is you realize that certain categories of systems, certain patterns, make it easy to get certain qualities out of your system, okay? So we're going to see more of this later. But this diagram that this table that's here shows from one of their early papers that, for example, data flow systems it makes it easy to change your algorithm, but it doesn't make it easy to change your data representation. That's what the minus means there. Something that didn't happen until 2010, which is really surprising it took us this long, is that up until 2010, we had only been talking about patterns in software architecture for runtime. So if you think about client server, well, that's a description of a runtime relationship. Your client maybe is running on the web browser and your server is running in your data center or something like that, okay? Or pipe and filter, you've arranged a bunch of little programs on a Unix or Linux command line and you're piping the data between them, okay? That's what the arrangement of that happens at runtime. The thing that they figured out in 2010, and it's an aha moment, and I have to admit, I was not ready for this when it happened, and I rebelled against it for a while until I was like, oh, this is the most obvious idea in the world. Those patterns occur on every single view, right? So you've got patterns of how you organize your modules. And in fact, one of the solid patterns, it arranges modules in a certain way. And then the same thing, you have deployment patterns today. So for example, red-green deployments is an example of a pattern that happens for how you deploy things. Finally, there were a bunch of insights regarding structure. The first happened in 1975, and this was so important, I'm going to read you a little quote from it because it feels like somebody wrote it today. Current languages discourage the accurate recording of the overall solution structure. They force us to write programs in which we are so preoccupied with the trees that we lose sight of the forest, as do the readers of our programs. Now, I can tell you that this represents a lot of my experience, right? I'm reading some program and it's an enormous difficulty to pop out of that. And I've seen people make mistakes where they didn't realize some code was going to be running on the server or not, or was going to be running on the client. In the 90s, we started to connect the idea of styles with qualities. And there was another abstraction that happened here that helped to structure things. Since time began, we have taken modules and we draw them as boxes, and we can put boxes inside of boxes. We can zoom in and out of the boxes. This is like completely normal. Of course, we think of things this way. But until the 90s, nobody had thought about doing the same thing for the communication between two different things. So it turns out we can do the same thing. Not only can we characterize the kinds of communication, say between a client and a server, and you'd say between a client and a server, you have a call return connection, okay? The client calls in and the server responds. And the rules of that connector say the server can't spontaneously generate things. Okay, now I know in real life, things we call servers sometimes push events over to say the web browser, but according to the style definition, that is a different kind of connector. That's an event connector, okay? So this was a real eye opener that the same way we can nest modules, we can nest connectors. And sometimes a connector that I consider to be call return can be implemented in terms of events. Okay, like if you think about it on the wire, you've got a bunch of UDP or TCP IP packets going back and forth, which don't obey events. They don't obey a client server. They don't obey a remote procedure call. There's a certain level of abstraction there. Okay, so that was the timeline of architecture abstractions. And I hope that that was helpful for you. If any of these are interesting, of course, you can jump back and find those original research. They're also sort of caught up to date in any of the modern software architecture books. Some references on that at the end. The thing that I'm hoping with all of this is that when you heard about these, you were reflecting on your current team. And something that you might have noticed is that like, some of my teammates still are not getting the interface versus implementation distinction right. Some of my teammates technically have an interface, but the interface leaks all the details across it and so forth as you march up these aha moments that people have had over time. So one way of thinking about progress is how far up that stack has your team gotten? I mean, to what level of insight is your team operating every day? Okay. Now we're in the third section of the talk. And in the third section, we're going to do a walkthrough of designing a system several different times using the same requirements. And we're going to see the troubles that can happen. The same set of requirements are the following: that you want to list movies starring a certain actor. You want to list movies released in a certain year. You want to list movies alphabetically. And then finally, you want to open up your program so that the customer can add new processing. So for example, the customer might have a ratings database that they want to merge in to the data that you've got. And you're starting with a file that has a bunch of JSON records, one per movie. And here's the part where this gets interesting. Imagine that the developer who just did requirement number 1 has moved on to another team or left your company, okay? So what you're doing is you're now having developer number 2 pick up the next requirement, and they have to just look at the code and see what happens. And what we're gonna try to do is we're gonna try not to change the architecture accidentally. We're gonna assume that the first developer was thinking something when they chose a certain architecture. And if I accidentally change it, I might accidentally lose the benefits that that person was depending upon. So let's give it a shot. Okay, our catalog of patterns is going to be 4 patterns, and we sort of alluded to some of these. The first one is pipe and filter, which you're familiar with like grep and word count on the Linux command line. This thing is really good for incremental processing, right? So it can process a line at a time, and it either emits a line or it doesn't. The bad of this is it's not terribly efficient, right? Because you don't get a chance to say operate on all the data at one time. Different kinds of efficiency problems, but it's not that it's terrible, it's just not super great for the best efficiency. There's a variant of this that sounds very similar called batch sequential. And the difference between pipe and filter and batch sequential is if you think about a compiler finishes one phase of processing, like tokenizing, before it moves to the next phase, which might be like building an AST. And so it runs on the entire data set to completion, and then it generates an output. Okay, so it can feel like pipe and filter, except that it does not operate incrementally. There's also another style called repository-based, which you've used a million times. Anytime you put stuff in a relational database, you're doing a repository style, and then you can generally do structured queries into that. The problem with the repository-based styles is that, as we saw with Rackspace, you got to load the data in first. So that may be an obstacle. And then finally, there's a pattern called Big Ball of Mud, which I highly encourage everyone to read this paper. There's a citation at the end. And the thing about Big Ball of Mud is there's no rules. And the problem with there being no rules is it doesn't really help you do anything in particular. It doesn't help you with incrementality. It's not particularly efficient, so forth. Okay, so walkthrough number 1. Let's imagine we give this requirement to our first developer to list the movies starring a certain actor. And then the developer scratches her head and says, this is sort of like the Linux command line. I can use a pipe and filter pattern, okay? And so it goes ahead and does that. And remember, the pipe and filter is going to process things incrementally. So as the records start streaming through the pipeline, it's going to emit the records that have the actor that's been requested, okay? And so this is pretty cool, thinks the developer, because we can even add third-party programs to this. Like, my filter for actors could be just one of many. So that developer goes away, and we give the system to the next developer, and this developer is asked, can you list the movies in a certain year? And this developer does the most obvious thing in the world. The developer just goes into the existing program and starts editing it. Okay, now that's not the way we were thinking about things in pipe and filter. In pipe and filter, you would create a bunch of little filters and you can compose them later on. Each one of the filters is independent of each other. But this developer has actually gone into the filter for actors and has changed it so that it also does years. So they're mixing the concerns. If we keep going like this, we just have one big program, one big ball of mud. So that's the end of walkthrough number 1, because we've accidentally wandered out of the style and we no longer get the benefits from that style. Okay, walkthrough number 2. Same requirement, list the movie starring a certain actor. Same thing, the developer does pipe and filter, okay? But it's different in round number 2. When we try to list the movies for a certain year, the developer goes, aha, this is a pipe and filter program. What I need to do is add a filter for the movie year, okay? So this is an edit that is within the style, and it stays within the architecture, which means that the third developer could come in and add yet another filter. So in fact, this is exactly what the third developer does. The requirement is to return the movies alphabetically, and the developer goes, aha, this is pipe and filter. I'll add a filter for sorting. But here's the problem, is that sorting is not incremental, at least as done on the Unix command line, right? In order to sort something, you need to have all of the data. You can't emit the results until you have all the data that comes in. In fact, you can try this at home. If you take a file or you take a stream and you start grepping across it, you can see that it outputs the lines, the things that it finds line by line. However, if you do sort, it waits and then it gives you all the results, okay? Now, what we've done is we've taken an architecture which was pipe and filter and turned it into batch sequential. Now, honestly, for a lot of systems, the distinction between pipe and filter and batch sequential is not that important. It's not a big deal. But just imagine there was some system that was taking an input continuously. That is, so if you think about Unix command line, there's no end of file character. There's just an open stream that's coming through. If you were counting on getting incremental results as they appear, if they come into the stream, well, you're going to be a bit bummed if somebody comes in and modifies the program and sticks in a batch job, right? Because all your incrementalism is gone. So, like I said, sometimes no big deal, but you need to be aware that you just changed the architecture right there. Okay, walkthrough number 3. The same requirement. The difference is this developer says, this sounds like a database problem. I could load all the different movie records into the database and then I can run queries. And I'll just write some SQL. So they use the repository pattern. And when the second developer comes in, there's already a database that's loaded with all the movies. And the requirement is to look for the ones in a certain year. It turns out this edit is super easy. You just add a where clause to the SQL in the program, no problem. How about the third developer? Again, you've got 2 different queries in the SQL and you've got a database. This developer does the same thing, just adds an ordered by clause in order to sort the records. Okay, this is looking like a cakewalk. Remember requirement number 4, which was to allow the customer to add new processing. So for example, they might have their own data set, which has like the number of stars for various movies, like the rating stars. And are we really going to let this customer go into our source code and like edit the SQL query? If they did edit the SQL query, would like the program work? I think, this is going to give us a lot of trouble. Like if we'd known that requirement, we would have chosen a different architecture, okay? This would have been a lot easier with pipe and filter. Point being is that some of these things are hard. You may not always know what requirements are coming out. And again, I'm not trying to tell you what the process is you should follow, but what I am saying is you can see that system is pipe and filter, that system is repository based, that system is a batch sequential system. And you can see the qualities that it makes easy or the qualities that it makes hard, okay? When you choose that, who has the titles on the team, what you call each other, whether you have stand-up meetings, all of those are interesting questions, but not related to this, right? Which is that the structure of your program, the architecture of your program will make it easier or harder to get these qualities. So please don't come away from this having a favored architecture, okay? That's not the point. There may be architectures that are more suited to your problem and architectures that are less suited. The important thing to look at them is, regardless of the functionality of the program, you want to choose an architecture that's tied to the qualities that you're looking for. So it could be security, or it could be speed, or it could be incrementality. Okay, so let's wrap up. In this talk, the goal was to explain software architecture without reference to you having had 10 years of experience in building lots of systems. I've done that by trying to talk about a case study that already existed with Rackspace. They built a server 3 different ways. I talked to you about the timeline of architecture insights and what we have discovered over time. And then finally, we did some walkthroughs of imagining that we were on a team and we had designed an architecture and where we could go off course as we accidentally changed the architecture, or we could have done it differently with deliberate changes. In any case, we saw what happened when we did change things. I hope that when you take away the lessons from here, you are going to have a shift in your perspective, right? The perspective change can make things that were previously complicated a lot easier to understand. So your old perspective might be, I need to bring 100% of myself to work. I need to roll up my sleeves and work very hard. And if I do that and I'm very smart, I'm going to be successful. Guess what? All of that is table stakes. The person next to you, the company next to you, they're all working very hard and they're all very sharp as well. The thing that you want to take away here is that the architectural perspective is that a suitable architecture makes certain problems easier to solve, and it can actually make other problems very difficult to solve. So getting the architecture right sort of makes a lot of those qualities come for free. You want the architecture to handle those problems for us. Another thing that you may be thinking today is, I'm going to get into my IDE and I'm going to design software inside the IDE. I do that all the time. Of course, you're going to continue to do that. But the thing that you might not have been doing up until now is that you're not using models that aren't the code itself. So the things that we've been looking at, the things that we've been talking about, are not necessarily visible in the code. So you need to go beyond the code. You need to be talking with your colleagues about abstractions, okay, that you are not going to see in terms of for loops and classes and functions. By the way, that's what every other engineering discipline does. Finally, you may have heard the expression, make it work, make it right, make it fast. I don't actually disagree with that advice, but there's a slightly different spin on this once you understand architecture, which is, if your intention is to actually make something fast, you may need to choose the right architecture that enables that to happen, okay? I've actually had some experience with a system that was designed for very high throughput, okay? That is, the total volume of processing going through the system was supposed to be very high. And then someone asked us to make it very low latency. And the problem is the things that are very good at very large amounts of data tend not to be good for very quick responses, okay? So the point is that it's a good idea to ask questions early and say, by the way, do you need, sub-millisecond responses? In which case, I'm going to need to think about that earlier as opposed to just hoping it works out. So we started the talk with this idea that Copernicus introduced a change in perspective. He didn't change the solar system, but what he did was he changed the perspective so that the solar system was simpler to understand. That's the kind of perspective that we are looking for software architecture. It turns out we're not the only ones. There have been an enormous number of people for the last 60 or more years that have been trying to understand software and trying to make it simple. There are a whole bunch of abstractions and insights here, and as we understand these, we start to understand software and it becomes simpler for us. I want to go back to the quote that I gave you at one point that was from Programming in Large and the Small. And I want to tell you something I didn't tell you before. That paper was written when people were still typing conference papers with typewriters. This is a scan from that paper. It was literally typed, like if you make a mistake, you got to retype the page kind of thing, okay? And they're saying these things about programs that are still true of so many of our programs today. So my question to you is, why is it that so many of our problems are the same as 1975, okay? Why is it that we are not taking advantage of the abstractions that we have and getting our perspective right so that we can work on bigger problems? The architecture brings us that kind of simplicity. The complexity in the code is already there, but the models give us the right perspective and avoid us bumping into our cognitive limits. I want to thank you guys for the opportunity to give this talk today. I hope that's been helpful for you. If you want to follow up some more, I'd recommend the Documenting Software Architectures book from 2010. The problem with this book is, number one, it says the word documenting in the title, which is going to scare you away. And number two, it should not be your first book on architecture, okay? The thing is, though, I think it has the best description of architectures. If you want a good introductory paper, I say one of the very earliest papers is fantastic. You can read it online. It's by David Garland and Mary Shaw, Introduction to Software Architecture. Also, here is the Big Ball of Mud paper, which, by the way, is not just about the Big Ball of Mud architectural pattern. It's actually about all the different context that describes why it is we still find ourselves stuck in 1975 development practices. And then finally, there's a longer architecture lecture, which I gave a while back on YouTube. It goes into a bunch of these topics in a bit more detail. So with that, I hope this was helpful. Thank you guys so much. And let me know if you've got any questions.
Thanks a lot, George. Really insightful, and also, yeah, thanks for the extra, let's say, resources or reading material. And I have to admit, I was scared at some point, especially in the last part with the walkthroughs, that it seems that there's always a moment when a new requirement comes in and then throws your whole architecture off balance.
Right. Yeah, again, I want to distinguish, well, first of all, tell me, how do I, on Zoom, how do I undo my presentation? How do I stop presenting?
Yeah, you can, you have the, well, share screen button. You can toggle it off. At least
I
for
do
me,
not
it's on
have
the
share
bottom side
screen
of the
button.
screen. I'm on
Okay,
Mac.
I'm gonna give up. I'm sorry. I'm like your
But
grandmother.
you
I
did it.
can't figure out Zoom. Apologies.
But now it's gone. It's okay.
Okay. So your question was, sometimes I get requirements and the new requirement is completely mismatched to my existing architecture. Is that right?
Yeah.
Yeah, that stinks, doesn't it? Yeah, but like it's like, yeah, it's like, what happens is, and you can see this in the rest of the world. There's lots of machines out there that have been modified in ways that you were like, well, if I'd known you wanted it to fly, I wouldn't have built you a bus and then we were bolting wings on it. I mean, that's not the right thing to do. So it's like, it's nothing special that we're in software development. I also completely agree with the idea that we should use prototyping in addition to models that I've been chatting about here. So, and again, this is the same thing that everybody else does. The only real thing that I would push on a bit is, I don't know of any other discipline, any other engineering discipline that would say, we only do prototyping or we only use models, okay? So for example, like, if you got to build a new kind of airplane, they do a bunch of prototypes to learn the different parts, okay? If you're doing something that's very well understood, they may prototype a lot less because they sort of are making incremental changes. If you change the color of a car, everyone understands, like, you don't need to build a prototype to change the color, okay? But if you're building a new kind of engine, I can guarantee there's a room in the back where they're tinkering around with engines for 6 months before they make the design in the computer and then push it out to production, right? So it's really about getting that balance right between the two.
Yeah, I think maybe also because you touched quite a bit on various views of the architecture and the system, and I think it's also important to make some of these decisions transparent, or most of the big ones, because I think that's sometimes doesn't happen. There are some decisions that are taken by, I don't know, parts of the team or just within the team and not with all the stakeholders. And then the problem is not that you get a new requirement that requires a big shift, but that some people are not aware of it and say, yeah, well, I would have let you know that this is coming up next.
Yeah, I 100% agree. I'm gonna 2 points on this. First is the things that I chatted about today. We're talking about architecture views. Now, those tend to be the whole picture, okay? But a lot of times in the way that we build software is we make decisions incrementally. And so, especially in the last 10 years, there's been a lot of movement towards, I really want to have an updated view, but if that's expensive to build, I can certainly write an architecture.md file, stick it in the root directory of my GitHub project, and every time I make a decision that would impact one of those views, an architecture decision, I write it down and say why. And it's right there in the code so somebody can jump in and find it. And I think that's hugely important. The second thing I would say, though, is that the decision records themselves, let me try this. Imagine that you had to draw something archaic, like a flow chart, okay? And you had 2 different tools. One tool has like a template, and it only allows certain kinds of things to be drawn and connected to the next kind of thing, right? It's enforcing some rules of flowcharts, right? So like no dangling connectors or no islands, like the whole thing has to be connected or something like that, right? Compared to you scribbling on a whiteboard, right? On a whiteboard, you can break all the rules. You can invent new symbols that don't exist, okay? So the thing about architecture decision records, and this is what Michael Keeling gets very right on this, is that it takes 6 months or so of mentoring. So let's say you understand ADRs very well and your colleagues don't. They will tend to write them in, because a word processor is an open, unstructured environment. They're going to write a whole bunch of stuff. And they're going to say, like, I like company X and I don't like company Y. And so we're doing company X. And you're like, yeah, but what is it about company X? Is it the fact that you don't like their licensing? Is it you don't like their design? What is it? Why did we choose these things? So with time, people can become very good at using the unstructured environment of, say, like a text file to describe things that are really relatively structured, okay? To get at the essence of the architecture, I have opinions and I wrote them down in a file. You see what I mean? See the distinction I'm drawing?
Yeah. Yeah, so then if I understand it correctly, in the beginning, or especially if, let's say, we know what we're doing, you need some constraints.
Yes, that's right. And in fact, Kevlin was chatting about extreme programming and Legos just a few minutes ago. And I don't hear this language as much as I used to, but when XP was very young, I remember the number one thing I kept hearing over and over again is that some people think that XP is being able to do whatever you want. And that is not the case. And they would say XP is more structured, is more disciplined than whatever you're doing right now. Okay, the difference is it's a different set of constraints. And we believe that it points you in the right direction. So you can only avoid doing certain kinds of architecture documents, which was popular back in the 90s, right? They said you can skip that if you have a certain kind of way that ideas are transmitted through the team, including pair programming and other practices, so that like if we're all on the same team, we keep that design in our head. We don't have to write a big paper binder full of documents and put it on the shelf the way that the battleship guys were doing in the 1990s.
Yeah, totally agree. And yeah, it's we could. I feel we could talk about this more and more. Unfortunately,
and that's why we have a conference. Thank you very much.
Yeah. So, but I think people will hate us if we skip another break like we did before. But yeah, thank you very much for being with us, George, and hopefully you'll agree to do it again.
I saw how you tricked the last guy, so you know, thank you very much. Let me know. I don't even know when the next one is, so like, yeah, well, I'll see if I can do it. Thank you.
Yeah, we'll definitely be in touch. Again, okay. Awesome session. Thank you.